guys, this is Mr. Millings, and today we're going to learn how to calculate the concentration of a solution in parts per million, and then we're going to go ahead and apply the concept of parts per million to some real world type of things. So let's take a look at what parts per million is. If we take a look right here, we have a little cube here, and this cube has the dimensions of 10 cubic centimeters by 10 cubic centimeters by 10 cubic centimeters. And therefore the volume of this cube, if we multiply these, is going to be 10 times 10 times 10, which is 1,000, right? 1,000. And then centimeters times centimeters times centimeters, which is centimeters cubed. So we have 1,000 cubic centimeters here, right? We have 1,000 cubic centimeters here, and that is going to be the same thing as 1 liter. Okay? These are the same exact volume or the same amount of space, except they are just expressed in different units. Okay, so if we fill this up with water, and this is an important concept to understand, if we fill this completely up with some water or some H2O here, what will the mass of 1,000 cubic centimeters or the mass of 1 liter of water be? Well, the mass of 1 liter of water is exactly 1 kilogram. Okay, so that's an important relationship to understand, that 1,000 cubic centimeters makes up a liter, and if you fill this up with water, 1 liter has a mass of 1 kilogram. Okay? Let's suppose I pull out one of these little units here. Okay, so we know that there are 1,000 of these little units that make up this liter here, and if I pull out one of these little units, what I will have, or the amount of space that this is occupying right now, is 1 cubic centimeter. Okay, 1 cubic centimeter. And if I fill this up with water right here, if I fill this up with some H2O, and I put it on a scale, it's going to have a mass of 1 gram, right? We know that 1 gram of water has a mass, takes up 1 cubic centimeter of space, or 1 cubic centimeter has a mass of 1 gram. That's the density of water, right? The density of water is equal to 1 gram per centimeter cubed, right? So for every 1 cubic centimeter I have, it's going to have a mass of 1 gram. And every 1 gram of water I have, it's going to take up 1 cubic centimeter of space. So that's an important relationship to understand. What's also important to understand is that there's 1,000 even smaller units that make up a cubic centimeter. And those are called cubic millimeters. And if I were to pull out one of these tiny little cubic millimeters and place it right here, it might look something like this. I've blown this up a little bit just so you can see it. In fact, it should be quite smaller than this. But this right here represents a cubic millimeter. A cubic millimeter. And once again, if I were to fill this up with some water and put it on a scale, it would have a mass of 1 milligram. Okay, 1 milligram. All right, so these are important concepts to understand, that 1,000 cubic millimeters make up a cubic centimeter, and 1,000 cubic centimeters make up this right here, this 1 liter. So let's think about this. How many cubic millimeters are there? How many cubic millimeters are there in 1 liter? So how many of these are there in this cube right here, this 1 liter right here? Well, to figure that out, let's think about this. There are 1,000 of these in this cubic centimeter, and then there are 1,000 of these cubic centimeters in this liter right here. So how do we figure that out? Well, we take 1,000 times 1,000, and what we end up with is 1 million. Okay, so there are 1 million cubic millimeters in 1 liter. So how does all this apply to the concept of parts per million? You're probably wondering that. Well, if this were some sort of dissolvable solute, like fluoride or chloride, which they put in tap water, or arsenic or lead, which are some contaminants that are in some of our tap water, or well water for that matter, we might want to know how many parts per million there are in that water that we're consuming. And if I place one of these inside of this cube right here, so I'm going to place one of these right here inside of this liter right here, I will have 1 part per million. That will be the same thing as 1 part per million. Okay, if I add 2 of these, I will have 2 parts per million, and so on and so forth. If I add 1,000 of these, I will have 1,000 parts per million. If I add 10,000 of these, that's going to be 10,000 parts per million. Okay, so that's an important concept to understand, parts per million. Furthermore, what you should know is that 1 part per million is going to be the same thing as 1 milligram per liter, right? 1 milligram here per liter, and sometimes you will see parts per million expressed in milligrams per liter. They're identical, they're the same thing. It's like saying 1 cubic centimeter of water is the same thing as 1 milliliter. They're interchangeable with one another. They're interchangeable units. So that's an important concept to understand as well. So let's take a look at parts per million, parts per billion, and parts per trillion and how they all relate to one another. Okay, so here we go. Let's suppose we have got a 10 gallon bucket here. So we have a 10-gallon bucket, and we're going to add just 1 drop of water to this 10-gallon bucket, or 1 drop of some sort of dissolvable solute, like arsenic or lead or fluoride or chloride or whatever it is. By adding 1 drop to this 10-gallon bucket of water here, you're essentially adding 1 part per million. The solution will now be 1 part per million in concentration. Okay? What if I add 1 drop to a 10,000-gallon pool, which is about the size of an average pool in the backyard? Well, this would be like adding 1 part per billion, or the concentration of this solution, if you added this little drop of water here, would now be 1 part per billion, 1 ppb. And last but not least, what if you add this same quantity, or 1 drop of water or dissolvable solute, to a lake? That would be like adding 1 part per trillion, 1 part per trillion. Okay? So understand that concept, that 1 drop in a 10-gallon bucket is 1 part per million, 1 drop in a swimming pool is 1 part per billion, and 1 drop in a lake is going to be 1 part per trillion. These are all about 1,000 times greater, right? This is going to be about 1,000 times the size of this 10-gallon bucket, or the 10-gallon bucket. And this lake right here is going to be about 1,000 times the size of this swimming pool right here. Okay, so understand those concepts. So let's take a look at how we can calculate parts per million. Okay, so how do we calculate parts per million? Well, parts per million is going to be equal to your grams of solute that are dissolved in the solution divided by grams of solution times 1,000,000. So here is our first little formula that we can use to find the concentration of a solution in parts per million. But what if we want to know the grams of solute? Well, to figure out the grams of solute, what we can do is we can take the grams of solution, which is on the bottom here, and put it on the top on the other side of the equal sign. And we can take the million here, which is on the top, and put it on the bottom of the equation on the other side of the equal sign. If we do that, we will end up with this formula right here to figure out grams of solute. Grams of solute is going to be equal to parts per million times grams of solution divided by 1,000,000. And last, if you wanted to figure out the grams of solution and get this all by itself on one side of the equal sign on top, you're going to have to take this and put it on the bottom over here, and you're going to have to take this and you're going to have to put it on the top over here. If you do that, you will end up with this formula. To get the grams of solution, you take grams of solute divided by parts per million times 1,000,000. So let's work with these 3 formulas here and work out 3 examples where we solve for each one of these. Okay, in example 1, it says a solution contains 5 grams of arsenic and 1,500 grams of solution. Calculate the solution's concentration in parts per million. Okay, so this has some real-world application in that you don't want to drink any arsenic. You don't want to consume very much of it. It's bad for you. So the question at the end of this little example here is, would you drink a solution of tap water that has got 5 grams of arsenic dissolved in 1,500 grams of the solution? Well, we'll figure that out after we determine the solution's concentration in parts per million. So to get the parts per million, we take the grams of solute divided by the grams of solution times 1,000,000. So to get the parts per million here, we're going to take the grams of solute. It says there's 5 grams of arsenic in this solution here. So we have 5 grams. And we're going to divide this by the grams of solution. It says there's 1,500 grams of solution right here. And last but not least, we're going to multiply this by 1,000,000. And when we put this in our answer, in our calculator, we will get 3,333.333 parts per million. Now I will tell you that parts per million, when we're solving for parts per million, that's typically expressed as a whole number. So we can round this to the nearest whole number, and if we round this to the nearest whole number, we will get 3,333 parts per million. So that is the concentration of this solution. So secondly, would you drink a solution that has this high a concentration of arsenic in it? Would you drink some tap water if it had this much arsenic in it? Well, if you did, you'd get sick more than likely. This is a pretty high concentration of arsenic in parts per million. Okay, so let's take a look at another example. In this example here, it says how many grams of solute are dissolved in 100 grams of a 1.2 times 10 to the second parts per million solution. Don't be scared, people. Just because you see scientific notation here, not a problem. As long as we just plug it into this formula here, we'll be okay. So to get the grams of solute, we're going to take the parts per million times grams of solution and divide it by 1,000,000. So to get grams of solute, we're going to take the parts per million. It says it's 1.2 times 10 to the second. We're going to multiply this by the grams of a solution, which says it's 100 grams. And we're going to divide this by 1,000,000. So we'll divide this all by 1,000,000. And if we do this and put this in our calculator, we should end up with 0.012 grams of solute that has been dissolved. So a very small amount of solute has been dissolved. This is a very, very small mass. Okay, so a very small amount of solute has been dissolved in this 100 grams of solution to give this concentration of 1.2 times 10 to the second parts per million. Let's take a look at our third and final example. Okay, in this example here, it says a solution's concentration is 12 parts per million. So here's the solution's concentration. If 30 grams of solute are dissolved in it, then determine the mass of the solution. So we want to figure out the mass in grams of the solution. So to figure out the grams of solution, we'll take the grams of solute divided by the parts per million and multiply by 1,000,000. So to get grams of solution here, we're going to take the grams of solute, which it says right here is 30 grams, and we're going to end up dividing this by the parts per million, which it says right here is 12. And we will multiply by 1,000,000. If we put this all in our calculator, it looks like we're going to end up with 2,500,000 grams. So the solution's mass here is 2,500,000 grams, which is a lot of grams. It's a lot of mass. Okay, so this is parts per million in a nutshell, and I hope this was helpful.